Hi everyone and welcome back to a new video about controller design, and we continue with the subject of Root Locus method. This is our example number 4. In this example I will discuss the design of a PD controller using the Root Locus method. We will of course again look to our calculations step by step, and we will verify our calculations using simulations in MATLAB. So let's look at the situation for this exercise. Now, the following situation is given. We have a system and it requires a PD controller, and we have the following configuration given. We have the controller in cascade with a plant and a unity gain feedback configuration. The plant transfer function is shown here, GP, which is then 1 over S times S plus 2, which has a pole at the origin and also pole at -2, which means this system, this plant, is already in this configuration. In the unity step configuration has a 0 steady state error. The controller, due to this, by the way, due to this pure integrator, the controller G of C is given by K1 plus K2S. The K1 is the pure gain part, which is the proportional part, and the K2S is the pure derivative part. So that S actually here in Laplace parameter means that there is a derivative action. So we have in total a PD controller. This is the transfer function we will use, and we will determine the K1 and the K2 according to the design specifications. So let's look at our design specifications. These are the following. We have the overshoot, which must be less than 4.32%, and we have a settling time with a 2% criterion must be less than 2 seconds. So we will use these design specifications and determine our design point from these design equations, and from there we will use the root locus equation to determine the K1 and K2, and we will do that step by step. So let's look at the solutions. What we do is first we determine the damping ratio zeta from the overshoot specification. Now the overshoot specification was given by this expression, which was 4.32%. We take the scalar value, of course, not the percentage, and we substitute that in this formula. Now, if you do that here, you will get very close to 0.707. That is our zeta, the damping ratio. Now, from the settling time, we can determine the absolute damping sigma of D. Now, since the settling time is 2 seconds, I can then use this formula, which is then sigma D is equal to 4 over the settling time given, 4 over 2, which is then 2. This is then the real part of our design point. What you also see in this analysis, I will take actually the edge of what is allowed here. So it is actually maximum this. So I will just take equal to that for the MP and also for the settling time T of S, which is just exactly 2, which is actually at the edge. So it's actually at the edge of what is maximum allowed. So this is the real part. Now, of course, we need the imaginary part for our design point. So this is our imaginary part, which is the omega D, which is the damped radian frequency. Now, if you use geometry, and we have discussed this many times in the previous videos, you can then have the sigma D times the tangent of arc cosine of the zeta. So you just first do arc cosine of the zeta, that is just first step, and then you have the zeta here, and then you take the tangent of that value, and then you multiply by the sigma D you have already calculated here. So this is actually shown here. So that is also equal to 2. So we have then the design point, or the dominant closed loop poles first actually from these are given by this expression. So S1, 2 is given by minus sigma D plus or minus J omega D. That is equal to minus 2 plus or minus J2. So we look at the root locus method, and for that we use the dominant closed loop poles. Now, these are the dominant closed loop poles that we use to determine the dynamics of our system. So if, of course, if this second order approximation is valid, we don't know yet. So we just assume at the beginning that the dominant closed loop poles determined by our specifications and also from the zeta and the sigma D and also the omega D, that this is what we can use as a approximation. So the complete system will be determined using these two poles. Now, from there, I will take one of them to use that as a design point. So I will use the one with the positive sign for the imaginary part. So the P1 is my designation for design point, and I will use that later on in the analysis. Now, if I make a sketch of the situation, what I have is the following. This is the complex plane, there's the sigma, and it's the omega, j omega. I have here the pole of my plan at origin, and it is the pole of my plan at -2, which is just shown here. This is my design point, which is also has a real part of -2 and has an imaginary part of 2. So you can see that the design point is shown here, and these two poles will have an effect, or will show shortly, have a phase contribution, also a magnetic contribution for this design point. But that will be determined and discussed in the next steps. So, how do we continue? Now, we need the root locus equation. So the root locus equation is first what we determine or set up, which is given in general form 1 plus the loop transfer function is equal to 0. So I need the loop transfer function, loop gain, LS, which is in our case very easily determined by looking at your diagram, and we had the controller in cascade with the plant and also the unity gain feedback, which is just, of course, just 1. And this is just the expression. Now, if I just write it out, you will have this expression, which is just the controller, PD controller, and it's just the plant. If I rewrite the controller in a different form, which will be helpful later on, if I just rewrite this, which is shown here, in this form, you can see directly what your 0 is. The 0 is, of course, when this expression is 0. That is actually determined by K1 over K2. So if you make K1 over K2 equal to minus of this value, or S is equal to minus of this value, you will have your 0. So if I use this expression, actually my loop transfer function, I will have then this one, and that will be a little bit simplified and written in this form. So I will use this. Now, then we have for our root locus equation the following. 1 plus this expression is equal to 0. Now, I can of course place the 1 to the right hand side, it will be -1. This expression is very, very important because from there we have this is of course the loop transfer function. From there we have the angle criterion or angle condition, and we have the magnitude criterion or magnetic condition. So the angle of this, you can see that actually from the right hand side of the equation, is 180 degrees or minus 180 degrees. Why? Because it is -1. It's just pure real part. Actually, it just doesn't have an imaginary part, but it is pointing in the negative x direction in the complex plane. So it just has a phase orientation of minus 180 degrees or plus 180 degrees. The magnitude of this loop transfer function is 1. You can calculate it by yourself. And that is also another condition. So you will use angle and magnitude criterion to determine the K1 and the K2 for our controller. So let's look at the angle criterion in more detail. From that, let's first sketch the situation. This is actually what we already had. So the 0 and the -2 for our open loop system. And this is our design point, which is now see as I've added the phases, so the phi1 and the phi2, I will discuss this shortly, and I've also added the 0 of my PD controller. I've already added the value of that, but that will be of course determined shortly. And the ZPD is the designation for the 0 of our PD controller. So this diagram will be discussed shortly in more detail, but this is actually what you should sketch for yourself to determine what the phases and the magnitude contribution is for each 0 and pole of your system. So this is the expression we have for each pole. That is a very important information. For each pole you have a negative phase contribution, and for each 0 you will have a positive phase contribution. So if I calculate phi1 and phi2, that will be some value, but I will take the negative of that one. And for the ZPD, which is the 0 of the PD controller, the phi, that will be just positive. So that's actually why this is minus phi 1, minus phi 2, and plus the phi of PD, which is minus 180 degrees. Now, since the PD controller has only a 0, which is shown here, and no pole, this is just also the 0 phase contribution. So that's just the phase contribution by the 0 of our PD controller. So this is actually the expression, which is then minus 180 degrees. So if I now look again in more detail what the phi 1 is the phase contribution of the plant at the origin s is equal to 0, which is just what is given already. Phi 2 is the phase contribution of the plant at s is minus 2, which is the other pole. And the phi PD, which is the phase contribution required by the PD controller, is in this case just the phase contribution by the 0 of the PD controller, and that's the required phase contribution of the PD controller with, of course, this one is the phase contribution by the PD controller 0. Now the phi 1 can be calculated easily using geometry here actually. What we want is, of course, this phase. If I want to calculate this phase angle here, I can say the half circle is minus or plus 180 degrees, and I can then subtract this angle. So what I do is I use tangent of this height divided by this length here, so that's actually arctangent to get to the phase. So I have an arctangent of the height, which is just 2, divided by this length, which is 2 minus 0, just for the completeness. That's actually what I just subtract from the 180 degrees, and that is phi 1, which is shown here, which is then 135 degrees. For phi 2, you can see that this is a special situation, which is actually a right angle, which is just exactly 90 degrees. So you can see that this is 90 degrees, which is 2 divided by the 0, which is of course undefined, but it is, you know, that is 90 degrees. Okay, that's the phi 1 and phi 2. Now we know what we have in our equation. We now use this angle criterion, which is determined then the phi z of PD controller. Now, if you just take the phi 1 and a phi 2 to the right hand side of the equation, you get this. If I just substitute the values for what I have for phi 1 and phi 2 now, I will have this value, and if I now do the math here, we will get exactly 45 degrees. That means the following. My PD controller, the 0 of my PD controller, must contribute 45 degrees. That is also that the PD controller must contribute 45 degrees. Now in geometry, since it's a smaller value than 90 degrees, I know that the 0 must be actually at the the left hand side of this vertical line of my design point. If this is, for example, 110, so larger than 90 degrees, then I know that it is between these two poles, or maybe all the way here. It depends, of course, on the value. So if you know that this is smaller than 90 degrees, you know that it is here. So maybe you have the question why I've placed the 0 here. That really depends on the value what you have here. So if you have the 45 degrees, that means this is 45 degrees. That means actually, again, using the geometry here, you make a triangle here, and then you know that this is 45 degrees, and you don't know this yet, but you can now determine that this is 2, and this is an unknown distance, and you can use again tangent. So I can then say this phase is equal to arctangent of this height divided by this value, which is still unknown, minus 2. I have done this here. So if you do the math here for yourself, just substitute the values for phi z of PD, I will have exactly 4. That is, this one is my 0 location, which is now here given as minus 4. And this is also the K1 over K2 expression in my PD controller, what was given initially in my in the assignment. So that means these two are equal to each other. That means K1 over K2 is 4, and I will use that later on in the expression for my controller. Now, at this point, I can already make the controller expression. I can say the controller, PD controller at the moment is K2 times S plus 4. So I have one unknown, which is the K2 still in our analysis. I know the ratio, but I don't know them individually. So we have used the angle criterion. We also need to use the MATLAB criterion to go to the individual values of K1 and K2. So let's look at the next step. So the magnitude criterion will allow us to use the following expression. The loop transfer function is equal to -1, but the absolute value of that one is 1. So I will use that one. Now, this was the value or the expression for our loop transfer function, which is of course now K1 over K2 given as 4. If I now look at this expression, the next is actually express the K2. I'll isolate the K2 in here to just actually the following action. You will have then the following, and then I will like to evaluate the K2 at the design point, which is of course -2 plus J2. So I will evaluate the K2 at that design, is this design point. It means actually the following. I just substitute for each place I see a S, I just substitute P1, P1, and P1. Just actually that simple. Then I will get the following. I will substitute, so -2 plus J2, here -2 plus J2, etc. also in the denominator. Now if you simplify this and you will take the magnitude of that one, of course, you will have the following expression. So you will have the square root of -2 squared plus 2 squared, which is just this part, and then -2 and this two real parts will add up to 0, which is actually specifically shown here, and this is just the imaginary part again too. And in a similar form, the denominator, I will also calculate the length of this one. Now if you do the math here for yourself, you will get exactly 2. That means the K2 is now determined, which is exactly 2. Now, since I know K2, having calculated K2, I can of course now calculate also K1y, because I already know the ratio of that one. We have already determined that from the angle criterion. So I can now say K1 is now 4 times K2. Now, since K2 is 2, I can say 4 times 2, which is then 8. Now, I have now all the necessary information for my controller. The PD controller is then given by, again, written down K1 plus K2S. What was K1? 8. What was K2? 2. Now, this is the expression. Now, of course, if I want to write it down in some nicer form, I can see the 0 directly, which is this one, and I have the following expression, which is then 2 times S plus 4. You can see directly that the 0 is at -4 for the PD controller, and the PD controller gain is 2. This is actually our final form. So the conclusion is the controller is given by 2 times S plus 4. Of course, we need to verify this using the simulations, but what we have initially from the analysis, the calculations, is that the controller is given by this expression. So let's jump to the simulation results. Now we have plotted a root locus plot and also the unit step response of the closed system with a PD controller originally designed for this one. So I have then this plot. What you see is the yellow region, which is the forbidden region, which will be defined by the damping ratio line by the overshoot, and also the absolute damping line, which is determined by the settling time, which is the vertical line. So I need to stay in my white area to be safe and also to satisfy the requirements for this exercise. But this is only valid if I have a pure second order system, or I can approximate my system by a second order system. So we will see what will happen. Now, if I look at the design point, or the close to poles, which are given by these pink dots, I have then the following location for them. So let's look at the location. This is the first second order dominant pole. This is the another dominant pole, and these has a location. You can see it here on the bottom. It is -2 plus 2i. That means actually what we have used for our design point. It is exactly correct. You can also see that it is at the edge of the intersection of the vertical line and also the damping ratio. So I expect that this might be the best solution, maybe not, but maybe at the edge of the solution. Let's look at the step response also. And the damping ratios, again, also shown here. So you can also circle that in red. You can see that 0.707, which is exactly what we had calculated. But this is the summary. If I look at my settling time, which is okay, 1.86 seconds, so it is less than 2 seconds, that is fine. But if I look at the overshoot, which is now 6.7%, which is larger than 4.32. And that is not actually what we have expected. So why is this the case? Now, we have, of course, a pole at the origin, which is now, of course, moved to here, one of them. And there is also a pole here. And we would like to approximate our controller or system in total by these two poles. But we have also the zero here. So if we forget about that one also. So you need to also consider the effect of that zero, which is not taken into consideration at the beginning. So we assume that the two poles here will do the job and will approximate our system accurately. But in this case, we will see that the overshoot is actually a little bit higher than expected. So we need to tune this. Now, one way to tune this is by, for example, changing the controller gain or changing the controller zero. So I will do that. I will change one parameter at a time, and I will see what the effect is. So in summary, for this case, overshoot is 6.7%, larger than what is allowed, but the setting time is okay, which is approximately 1.9 seconds, which is less than 2 seconds. So let's then look at our tuned system or tuned PD controller. I first changed the zero location. So I've moved the zero from -4 originally to -6. So I have to place it to the left side of the complex plane. Now the solution is this. I have now the two second order poles here, which are actually more in the yellow region. So you might ask, is it the best option? We will see what's happening here in the settling time. It's 1.5 approximately, so it is a little bit lower. The settling time was already okay, so it is a little bit smaller. Okay, that's maybe a little bit more improvement, but I can see that the overshoot is now even higher. So it is a 13.7%. So this is definitely not the way to go. So if I again place maybe the zero all the way to the left, maybe at 8 or -8 or -10, maybe I get even worse results. So this is definitely not the best option, and I can see that this tuned PD controller is worse than the originally designed PD controller. Of course, it is a little bit faster in terms of settling time, but the overshoot is definitely not better. It is even worse. So we need to tune this again. So what I have done now is I have moved the zero of the PD controller. In the next phase, next step, I will now keep this again at 4. I will just adjust the PD controller gain. So let's look at the next results. Root locus plot and a unit step response, of course, of this tuned PD controller, but I have now changed or decreased the PD controller gain from 2 to 0.75. So I've just, of course, kept the zero location at -4, that is unchanged as original, but I've changed this from 2 to 0.75. Why I did that is the following motivation. I know, okay, the zero location shifting, that doesn't really help, but I know that my settling time was fine, but the overshoot was a little bit larger. So by placing the gain of the P controller, actually of the total controller, if I make it a little bit lower, maybe I can also lower the overshoot. That's actually the motivation to go for the lowering the controller gain and not increasing the controller gain. So this is the result, and I can see that the poles, the dominant closed loop poles, assumed dominant closed loop pole, are now here. But if I look at the response, I can see the settling time is now 1.8, okay, a little bit larger than what I had in the tuned version for the zero shifting. That's still fine, but I can see that the overshoot is now, so that's fine, and I can see that the overshoot is now 1.93%, almost 2%, but it is smaller than 4.32%, so that's also fine. So in total, I can see that this overshoot is, in this case, fine, and also the settling time is less than 2 seconds, that's also fine. So we can say this is one of options you can use as a PD controller for this design. what we see, and I will make a summary in the next discussion, but you see that the rise time is actually much larger for this system than the other two. So let's look at the summary. The summary of the result, and I have now plotted all the unit step responses for the closed-loop systems. So the T1 is the closed-loop system, which is shown here in blue, of the closed system with the original design PD controller. The orange one, T2, is actually the one with the PD controller tuned by shifting the 0 to the left-hand side. And the orange line or a yellow line is the one where we have adjusted or decreased the PD controller gain from 2 to 0.75. And T3 is then the closed-loop system using that controller. Now you can see, if I now make the summary here, which is shown here, if I have again the PD controller 0 shifting, and this is the PD controller gain decreasing, you can see this is the original, which has a 6.7%, but this is the shifted version of the 0 that is much larger, almost maybe more than twice increase in the overshoot, a little bit decrease in the settling time. That's definitely not the best option, but you can see the rise time is decreasing. But if I go to my end result, which is this controller, I can see that the overshoot is okay, almost 2%, and also settling time is 1.8 seconds. But I can see that the rise time is almost 1.3 seconds, which is way larger than these two values. So it already increases more than twice actually in rise time. So the speed, the initial speed actually of your response of your system is definitely not as good as these two systems. But that wasn't really the requirement. So requirement was actually the settling time and also the overshoot. So that means for our case, this is definitely one of the options to satisfy our given specifications. So this is now done for this PD controller design. Again, as you can see, our initial design PD controller might not be the best solution. We need to always check that by simulating our controller in, for example, MATLAB, and then tune the controller, of course, using your motivation for why you do that. If you want to shift your 0, you need to, of course, have a motivation for that one, also for the gain and also for other parameters. Thank you very much again for this. I hope this clarifies the situation even more in more detail about the PD controller design. I will continue in another video about the PID controller design. If you have a question or a comment, please let me know and I will try to answer it as soon as possible. Thanks again for your attention and see you next time, and take care.